When I was at school doing my physics homework, I would spend a few pages showing my calculations, coming up with an answer that I thought was the right one. It was, say, a number like 9.81. And I'd hand the work in to my teacher, and he'd scroll across the bottom, 9.81 what? Elephants? And it was very irritating at the time, but he made a good point that units are essential to any numbers that we deal with in engineering and therefore in software development. The largest scale example of this going wrong was back in 1998 when the Mars Climate Orbiter, which is a probe supposed to go into orbit around Mars, was sent from the ground station an instruction for a thrust in pounds, and it interpreted it as a thrust in newtons. And given the ratio of pounds to newtons is about 4:1, that was quite a big difference, and nobody knows quite what happened to it, whether it crashed or disappeared off into space, but it was certainly a major disaster due to a mismatch in the units being used. When it comes to computing, whether or not we are worried about units varies depending on what type of application we're dealing with, but probably the most common one we come up against is units of time. And very often we'll find units of time measured in milliseconds, which is all very good if you're, say, doing some kind of animation on a desktop application. Whereas on the other hand, if you're trying to do a timeout for a cache, you might be more interested in hours or even days rather than milliseconds. So it does make a difference. And if you get the numbers wrong, maybe your satellite doesn't crash, but it can still be quite serious. So what I've got here is actually a program written in C++. What I'm going to show you will work in any strongly typed language, so C# or Java will work just as well, except at the very end I'm going to show you a new feature that came in C++ 11, which really makes this sort of thing very, very much more natural to program. And although the basic ideas are common to all languages, if you are a Java or a C# programmer, this will just give you something to be a bit envious about in C++. So what I've got set up here is just a simple weighing machine. So we can see if we look at the main program that we declare this weighing machine, we then add in a number of different masses and then get back the total mass. And immediately we can see the problem here, that there's no idea what units these masses are in. If we look at the way the weighing machine works, we've got a vector of the individual items, but they're simply declared as doubles. We've got a get total that returns a double, and we've got this add item that has a double that it's simply calling mass. And therein we can see the entire problem, that we've got no clue what to put in here. You could do a few helpful things. You could maybe actually in the name of the parameter indicate that it was supposed to be in kilograms, but it's not going to enforce anything. Nobody's obliged to read that. You're not obliged to, well, not even obliged to put in a parameter name at all in C++, or you could put one in that's rather too general, like just having mass in there. So we need to find a robust way to make sure we know what units we're dealing with. If we look in the CPP file, you can see that on the add item, we simply pop that into the vector and then return this so that we can chain those calls together. And then to get the total, we have this accumulate function from the numeric header file that adds them all up. And if we run that up, then we should see that we get the result of 308.17, but as my physics teacher would have said, 308.7 watt elephants. We've got no idea what's going on. So not helpful, error prone. If this software were in the Mars Climate Orbiter, then it could cause real problems. So we're going to make it so we've got a nice robust way of getting this all to work. First thing we're going to do is we're going to add a base class for handling mass. So we'll add a class here, I'm going to call that mass base, and then click OK on that. And the very first thing I'm going to do, I want to make this mass base an abstract base class. Now in C++, we don't actually have a keyword abstract. The way we normally make something abstract base class is to give it a pure virtual method, but we don't need that here. So what we're instead going to do is just a little trick, which is to make the constructor protected. And therefore only derived classes will be able to call the constructor, and that effectively makes it an abstract class. The other thing we're going to put in the protected section is the actual place we're going to store the mass. And at this point we can make a decision as to what units we're going to store it in. And because I would normally be using SI units. I'll just use the SI base unit for mass of kilograms. But if you wanted to use pounds or whatever there, it's entirely up to you. It really makes very, very little difference as to how the system will work overall. But I would choose something that makes your formulae and your equations convenient. So if I'm using SI units and I'm using, say, E equals mc squared, then m wants to be mass in kilograms. So it just makes life easier to put that in there. And then the other thing I'll do is in the constructor, I will take that value of kilograms and I will simply enough just initialize that in there. No need to worry about putting it in the CPP file because that one is so very simple. And so there we've got our mass base. Now the next thing we're going to do is we're going to go back to our weighing machine, and instead of having that dealing with doubles, we are going to replace everywhere that it refers to a double with one of these mass bases. So we'll do a hash include and get hold of mass base, and then that's going to go in there and in there, and everywhere we've mentioned a double, even on that get total, we replace it with a mass base, because the problem is doubles aren't giving us enough information. They simply give us a number. We don't know what units that number is. In fact, we don't even know what type of quantity it is. A double is just as much used to store, say, a distance as it is to store a mass, so it's not got enough information, whereas mass base has got everything that we want. We'll need to go to the CPP file and make the same replacements there. So that's mass base, and that one is mass base. And that then will give us a couple of problems with this accumulate. The first and most obvious one is if we're going to accumulate, we need to be able to add our masses together. So the first thing we'll do here is in the public section, we will add a plus operator. So plus operator is going to return a mass base. It's going to be called operator plus, and it will take as a parameter a const mass base reference called mass, and it will itself be const because we're not going to change this mass by adding another one to it. Give that a body, and then all we need to do here is we need to say we're returning our own mass in kilograms plus mass dot mass in kilograms. And that's really, or that sort of place, is the only place we're ever going to worry about what units we're dealing with inside methods of the mass base class, which is where we know we're dealing with kilograms. And it's not just for addition, but any formula we've got, say we need to multiply mass by velocity to give us momentum, we'll do that on the base classes where we'll know what units our mass are in, what units our velocities in, and return momentum in a known unit as well. So we've put that in there. That will partially solve the problems that we've got in the accumulate. But the other thing, as well as needing a plus, it also needs this starting value. And 0.0 is obviously a double. We need to have a 0 value for our mass. And so we're going to do that by also in the public section here, we are going to put in a const static mass base 0, and then because that's static, we'll have to define it in the CPP file. So just a bit of fiddling around there, and initialize that to 0 kilograms in this case. But of course, when you've got a value of 0, it's 0 whatever unit you're dealing with, so it doesn't really matter about that. But that's our 0, and then back in the weighing machine, we'll replace that with mass base : 0. And then the next thing we need to do is actually start putting in some derived classes for this mass base, which are going to represent our specific units. Now, the first specific unit we need is going to actually be the kilogram. So although it's pretty obvious we're already storing kilograms in the base, we want to have a separate class for this. So we'll have a class called kilogram. And these are going to be really, really simple. So we can make them inline. They don't need a CPP file, just a header file. And we'll let the code generator derive that from mass base. So I'll click that. And then all I need to do is in here, give this a public constructor, which is going to take our number of kilograms kg, and then pass that down to the base class. And because this is kilograms, actually nothing really much happening in there at all. We just pass the kilograms straight down. We'll see, however, when we get onto a different type of unit, this gets more interesting. So let's now add another unit. In this case, we will have our ton. So metric ton, still pretty simple, 1,000 kilograms in a ton. Still going to be derived from mass base and inline it. But this time, what we need to do is have our public constructor, and that's going to take a double that we'll call tons. But then when we pass that down to the base class, we need to do the conversion. So the base class has always got to be dealing with kilograms. So here we take tons times 1,000. So that will give us the mass converted on construction into kilograms. Then let's just add one more. They could go on for as long as you like with this. Slightly more complicated. We're going to have a class called pound, again derived from mass base. Again, inline it. And so now we're going to have public constructor takes the mass in pounds and then calls the base class, converting that into kilograms again. And we can see here that the conversion rate is 0.453592. So if we take pounds times and then that value, that will be our conversion into kilograms. Ideally, you're probably going to want to put that kind of number into a constant, not just hard-coded in there. But bear in mind, the only place this should be used is within the pound class. So it's not like more traditional programming where you'd be using your conversion rate all over the program. The conversion rate is isolated inside the pound class, and that's the only place it's going to be needed. So that's created our three specific mass types. And so the next thing we need to do is, if we go back to the main program, we can see obviously it now no longer accepts doubles because we don't know what doubles mean. So what we need to do now, we're going to need to include our individual mass types. So we'll have one for kilogram, we'll have one for pound, and we'll have one for ton. And then all we've got to do when we add them is wrap them up in the appropriate type. So if we want our 100 and 100.5 to be in kilograms, we can put that in there. We can have 2 tons, put that in there, and we can have 205.67 pounds, put that in there. And that leaves us with one last problem, that our get total, remember now, is returning a mass base, and Cout has no idea how to deal with that. So the normal thing, we've got to give our mass base a insert operator. So we're going to need to say hash include of IOStream, and then we'll say declare as a friend so we can access the protected data, and it's going to be std : ostream by ref, that's the return type, and then it's called operator double left arrow, and then it's going to take 2 parameters, the ostream, so that's in our case going to be cout, but it could be a file stream or something like that, and also it's going to take an actual mass base object, and then we simply return os insert, and here we're going to return mass.m_kg. But we're not just going to do that, because once again that would be a number and my physics teacher would be asking me how many elephants. So we put on there the fact that that is going to be kilograms. So it's absolutely clear what's going on. And that should mean that our output of get total is now happy. give that a quick build, see how it's working. So that's built okay, and if we run it, then we're getting 2193.79 kilograms. You can do the maths to check that's right, but we've done 2 tons, so that's our 2,000. Then we've got 100, then pounds, roughly 500,000 kilograms. So that looks about right. And we can see 2 really nice things there. One is that the values we've put in, we have to specify a unit. We can't just put in numbers, we've got to specify a unit. And then when we get the result out, we're getting the result with units attached, so we can see we've got kilograms. Let's just take that a couple of steps further. One is all very well having get total telling us it's kilograms, but just like we'd like to be able to input the data in whatever units we've chosen, we'd like to get that out. So I'll show you an example of just one of these. Let's go to our pound class, and if we want to be able to have output in pounds, then what we essentially need to do is take from our mass base, let's just copy that operator and paste it into our pound, and then a couple of changes. We're going to need to make it take a pound as a parameter, call that pounds, and then what we're going to output is the mass in kilograms, but then divided by the conversion rate. As I said, probably best to make that a constant, but you can see here, as I mentioned, it's still going to be isolated for the pound class, just for those 2 operations going in one direction and the other. And then we will put the unit so that it's always displayed with the appropriate units. And then back in the main program, all we should need to do is wrap up that get total, which remember is coming out as a mass base, convert it to pound or to whatever unit we want the results displayed in. We can see an error there because we've got to also on here give this a copy constructor. So we're going to have pound, which is going to take a const mass base ref, and then just call the base class copy constructor. So that should be happy. Back in units, that's now happy. Give it a test build. And then when we run that up, we can see it's now given us the result in pounds. And if we just put the 2 side by side, so there's the costs, there's the mass just in the kilogram unit, and there it is in pounds. And so if we run that up, we can see, as I said, a ratio of roughly 2 to 1 kilograms to pounds. So it looks like that's working correctly. And all of that up to that point you could do in C# or in Java. Slight differences obviously, but the same basic idea would apply. The next bit, however, is something unique to C++, because what C++ added in version 11 was the ability to have what's known as literal suffixes. The place that this is most obvious in the C++ standard library is actually to do with time. So if I just do a quick include, if I include, and then let's have the thread library, and then I'm also going to use a sub namespace, which is std : chrono for time. And sort of thing that you very often want to do with threads in a very simple example is just delay things for a bit, send the process to sleep. So what I'll do here, I'll say cout, and then we'll just have sleeping. And then I'll say this underscore thread : sleep 4. And this is the sort of situation when I was talking about earlier that you might have had to put in a number of milliseconds and make sure you got a number of milliseconds, or if you wanted a longer sleep and you wanted a number of seconds, you've got to multiply 1,000, all that sort of thing. All we need to do here, you can see, it doesn't take a double or an integer or anything, it takes one of these durations. And the way I can do that is if I just type 1,000, doesn't like that, But if I type 1000 ms for milliseconds, and that ms has come from this chrono namespace, then it's perfectly happy and we've specified milliseconds. And so if I run that up, then we can see sleeping about a second, and then it outputs the result. But if I'm not happy using milliseconds, I could do something like this. I could say 7.5 seconds, so S for seconds, obvious enough. And now if we run it up, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi. I was counting a bit fast, but we got the results coming out there. So it's really nice that you've got various one of these, seconds, milliseconds, also microseconds, though microsecond, because you don't have the mu symbol, it's actually U, which looks a bit like a mu, but all sorts of things we can do there. And because this feature is available in the library for things like time, it's also available to us as programmers for things like units. So once again, let me just show you this on pound. What we have to do with this, it can't be declared as a member, but always a good idea to do it in the appropriate header file. And so we're going to have an operator. This is where it gets a bit weird. It's always an operator called empty double quotes, followed by the way you want to represent your unit. So I want pounds to be LBS. And another slight oddity, if we're defining these for ourselves, then the rule is they've got to be preceded by an underscore. Otherwise, it just gets too confusing, essentially. The ones in the standard library, like we just saw for seconds and milliseconds, they don't have to have the underscore, but for our own, we have to do that. So what's this operator going to do? Well, the idea is for it to give us one of these pound objects converted from simply a double. But you'll notice it doesn't like that, because another of the rules with all of this is for whatever group of types you're dealing with, we're dealing with floating point numbers, you have to declare the largest of all of them. So actually we've got to have a long double here. Otherwise you would have to write one of these for a float, another one for a double, and another one for a long double, which would be a bit redundant. Similarly, if you're dealing with integers, you don't want to have to write one for a short, one for an int, and one for a long, and one for a long long. You just did all for a long long. So having done that, then the code's very simple. We just say return pound, and then pass in the value. So we've already got a constructor that creates a pound like that, and that should be perfectly happy. And then all that we have to do is we have to go back to our main program, and in here we apply to the literal that we're going to say underscore LBS, and you can see it's perfectly happy. And so we've got our 205.67 pounds, exactly the same as using the pound constructor, but a much neater way of doing it. And if we run that, then we should see that's all working perfectly okay. So let's just fill in those gaps there. So let me take the one from pound and pop it into ton, which we'll call T. I'm going to take a ton and a ton, and then we'll do the same with our kilogram. And call it underscore kg. And then simply enough, back in our units, we can just say 100.5 underscore kg to underscore t. Notice a slight problem there. I've actually got to put in 2.0 t because I'd specified that this takes a long double. So if I really wanted to be thorough, I could have done integer versions of these as well, or you may prefer your users to have to put the 2.0 in. But either way, much more legible. We can see we've got kilograms, we've got tons, we've got pounds, and when we run that up, then we've got the same sort of results. We don't need that sleeping anymore, but that doesn't matter. So what we've got there is a very robust way of making sure that you get the correct units passed in, and when you get results reported, you get them reported not just as a number, but with the appropriate units on the end, so everything is legible, everything is clear. As I mentioned, Most of that, all the class stuff, will work with Java and C# as well, but it's only in C++ so far that we've got these really nice way of doing literal suffixes that allows us to have very, very easy to read code when we're dealing with units. If you've got any questions, pop them in the comments section below. Also have a look in the comments section. I'll put a link to the completed code so you can have a play with it yourself.